Before they could build the crane, they had to rebuild the ground. The machine was too heavy for ordinary soil, not slightly too heavy, it would sink. So before a single component went down, engineers poured a custom concrete foundation, mathematically designed to distribute a load the actual Earth could take. And at that point, it hadn't lifted anything. Workers at the site just call it Big Carl. It stands 250 meters tall, it can pick up 5,000 tons and rotate it in a full circle, it weighs 11,000 tons standing still, and it was invented from scratch, because when the people building one of the largest nuclear stations in Europe went looking for the machine that could do the job, they found out it didn't exist yet. This is what that looks like. Nuclear power stations are not assembled the way most buildings are. Most construction makes sense. Things arrive on site and go up piece by piece from the ground. That works for everything made of components a crane can manage. A nuclear reactor is not that. The components at the heart of the reactor, pressure vessels, steam generators, the enormous steel structures that contain an active fission reaction cannot be manufactured on site. They are built in controlled factory environments, clean and precise, where every single weld is inspected by someone who puts their name to it. You cannot do that working in a field in Somerset in November with the rest of a construction site running around you. So the components are made somewhere controlled, tested until everyone is satisfied, and then shipped. And then someone has to lift them. A steam generator at Hinkley Point C, the nuclear station currently under construction in southwest England, weighs around 1,000 tons. You cannot lift that with a standard crane. You also cannot lift it with 10 cranes working in coordination, because coordinating 10 independent lifting points on a single object stacks risk with every additional hook in the chain. One hydraulic failure in one crane at the wrong moment is a disaster you cannot recover from. What you need is one machine, something that takes the full weight alone, moves it through the air with total control, and places it down exactly where it needs to go. When Cerens, a Belgian heavy lift company, started working out what Hinkley Point C actually required, they ran into a problem. The machine for the job did not exist, so they built it. It's a ring crane, not a tower crane pointing upward from a fixed base, something completely different. The base is a circular track, hundreds of meters in circumference, set into that specially engineered foundation. The crane rotates around this ring a full 360 degrees, which means it can lift a component on one side of the site and deposit it somewhere entirely different without moving a single meter in any direction. The load travels, Big Carl stays. The main boom reaches 160 meters. With all auxiliary systems in place, the full structure tops out at around 250 meters, roughly the height of an 80-story building. Standing at the base on a clear day, the arm goes up and disappears. Not slowly, it just ends somewhere you have to tilt your head back to find. Maximum lift, 5,000 metric tons. The Eiffel Tower weighs around 7,300 tons. Big Carl can lift roughly 2/3 of it in a single movement on a single hook. Rotate it in a complete circle and set it down with precision that would be impressive at a tenth of the scale. Here is what makes it genuinely strange. Big Carl weighs 11,000 tons. The crane is heavier than most of what it lifts. The counterweight system at the rear, the steel ballast blocks that stop thousands of tons of swinging load from pulling the whole machine forward, runs into thousands of tons on its own, just to keep the physics from going catastrophically wrong. The engineers working on the SGC-250 were not improving an existing crane. There was no previous version of this to improve. They were solving a set of problems nobody had solved before, for a machine that had never existed, because the work it was built to do had never been attempted at this scale. One of the core challenges was not what it had to lift, but what would happen to the crane itself during the lift. A structure this top-heavy, rotating while under maximum load, requires a stability calculation so involved it took years just to get the numbers right. Big Carl cannot travel. No engine, no wheels, no way to move it from one place to another in any normal sense. It only exists when it is assembled, and it can only be assembled on site, so it arrives in pieces. Hundreds of separate components delivered across hundreds of truck movements over several weeks. The trailers carrying the heaviest sections have more axles than most people have ever seen on a single vehicle. They are computer controlled to spread the load wide enough that the road surface does not fail underneath them. That's not a precaution. That is a living engineering problem being solved in real time on every delivery run. On site, the ring track goes down first, embedded into the concrete foundation, then the rotating platform. Then the mast climbs upward, section by section, lifted into position by smaller cranes that are themselves enormous. Then the boom, the counterweights, the rigging, the control systems. Months of assembly before a single lift. What does not stop throughout any of this is its alignment checking. A ring crane that is fractionally off level cannot do accurate work. The tolerances being maintained across this structure are measured in millimeters on a machine that weighs as much as a warship. There is no version of close enough. The numbers are the numbers, and they have to be met, or none of what comes after is possible. When Big Carl lifts something, the preparation takes longer than the lift itself. Rigging is calculated and certified specifically for each load. When speed is checked, there's an operating limit, and at 250 meters, what reads as mild at the ground level is a completely different situation up at the tip of the boom. The ring position relative to the landing point is confirmed. Every person inside the lift zone knows exactly what every other person is doing, and what the contingency is if something changes. Then the load rises. The motors are quiet. That catches people who see it for the first time. A machine this large, moving this much weight, does it with kind of a slow patience that has nothing to do with struggle. The component clears the ground, the arm swings through the arc, and at the other end, without drama, it meets the landing point. No overcorrection, no adjustment, first time, right place. A multi-crane operation would take weeks to coordinate for a lift like this, with risk stacking at every stage and the consequences of failure too large to fully plan around. Big Carl does it in hours, quietly, as if lifting 1,000 tons through open air is just the job, which for Big Carl, it is. Getting Big Carl to a construction site requires hundreds of separate truck deliveries and months of assembly before it can touch its first load. Once standing, the structure reaches 250 meters and can lift 5,000 metric tons, though the crane itself, carrying nothing, already weighs 11,000 tons. It outweighs most of what it lifts. The ring track, the counterweights, the specifically engineered foundation beneath it, all exist to manage the consequences of that one fact. Hinkley Point C will power around 6 million homes when it's finished, and Big Carl is there because the components inside it are too heavy for anything else on Earth to place. When that work is done, it comes apart, goes back onto trucks, and gets reassembled wherever the next job is waiting that nothing else can handle. Look at the component, look at the crane. The crane is heavier. Nobody tells you that. An 11,000 ton machine, assembled from scratch in a Somerset field and named after a bloke called Carl, built entirely to move things lighter than itself. When Hinkley Point C is finished, it packs up and goes somewhere else. There is always another impossible lift. Most people drove past that delivery trucks without a second thought. Subscribe if you want to keep seeing what most people miss. We'll see you next time.